Hi, I'm Ingrid Halverson. I'm from Wayzata, Minnesota, and I'm a robotics engineering student.
I'm Danny Ezzo. I'm from East Lansing, Michigan, and I'm a mechanical engineering technology student.
I'm Parker Courte-Rathwell. I'm from Quebec, Canada. I study mechanical engineering and exercise science, and together, we're Moonstep. Human space travel is on the brink of making it back to the moon. And human space travel offers a lot of opportunities for developing technologies and reinforcing our knowledge with how people want to move on the moon. This research with Moonstep will allow physiologists to better understand how we accomplish those movements, and we can also help bipedal motion engineers understand how they can simulate the environment.
The Hypo-Gravity simulator is designed around the goal of researching metabolic costs of different lunar gait patterns. Moonstep approaches this goal by utilizing a combination of elastics that can provide an upward force corresponding to 5/6 of an individual's weight, and participants in this simulator can range from 100 to 200 pounds and measure 5 feet to 6 foot 4 inches.
To accommodate the weight of different volunteers, we use a configuration of 3 to 5 elastics. We use 4 different size elastics that, when stretched to 90 feet, equate to 5, 10, 25, and 50 pounds of pulling force.
So elastics are non-linear systems. However, if your operational range only represents a small percentage compared to the total stretch range of your elastic, the amount of force deviation that happens in that operational range is almost linear. And that's what we're trying to capitalize on in our system.
In order to verify if our elastic concept works in practice, we use a variety of sensors to collect force and acceleration data. To measure the offloading force, we use a load cell in series with a test participant. Simultaneously, we use an inertial measurement unit, or IMU, to collect the vertical acceleration data of the participant. These sensors use a network of ESP32 microcontroller boards to wirelessly transmit the data for further analysis. Both of these measurements will help us to tune our system to be more accurate to a moon gravity environment.
We defined that in order for our frame to accurately simulate astronauts' movement in space, we need to allow for the same 4.5 feet of vertical displacement we saw in clips from the Apollo missions. In order for the offloading force during the 4.5 feet of displacement to be approximately linear, we needed to pack 90 feet of elastics within the height and length requirements of our lab. That is why we chose to extend the elastics around a series of pulleys within a frame that could be disassembled and moved around campus. Our design is a product of existing simulators, using some of the features they did well and improving on some things that they didn't do so well. Our frame is portable, cost-effective, and provides a more linear force in comparison to some other current designs out there.
The biggest challenge that we've had in this project is having the elastics act the same way inside the frame as they do outside the frame.
The problem this challenge exposes is mobilizing the elastic around each pulley. Currently, concentrations of stress on the elastic causes a significant amount of energy loss, resulting in the unanticipated behavior. After analyzing our data, we realized that our system isn't utilizing the full 90 feet of elastics, thus making the system less linear and less accurate than we had wanted.
We'd like to thank our advisors, Dr. Chen and Dr. Elmer, as well as members from the ROLAC Lab, Anders and Chibiyogi, who provided an incredible amount of insight and support during the past year. None of this would have been possible without the support of the National Aeronautics and Space Administration, who provided us with a grant. To NASA, we thank you. We look forward to where this project will take us.